Here we are with the video for Chapter 8, Section 2, Gas Laws. The learning objectives are listed here for you. Please pause the video and write those down in your notes. Okay, in order to describe a gas completely, we are always going to encounter four variables. Four variables are always in play when I'm talking about a gas. Those are the amount of gas. The symbol used to represent the amount of gas is a lowercase n because it'll be in moles. The volume of a gas. Remember, volume of a gas is the volume of the container in which the gas is held because the gas is in constant random motion and fills its container completely. Temperature, represented by a capital T. Now, while temperature is often measured in Celsius, it needs to be in Kelvin when put into a gas law. So when we are using calculations with temperature, we need to have it in the Kelvin temperature. So you can see, please take a minute and jot down these quick conversions. Basically, I'm just adding 273.15 to my Celsius temperature to get Kelvin. And finally, pressure. In the first video from this chapter, I spent a lot of time talking about pressure and the definition of pressure, which is the pressure comes from the collision of the gas particles with the walls of the container. Now, the gas laws are the mathematical relationships between these four variables that I've just outlined here for you. There are a whole list of gas laws. Here they are right here. Gay-Lussac's law, Boyle's law, Charles' law, Avogadro's law. So basically the way this worked is we have these four variables: amount, temperature, volume, and pressure. And each gas law is a mathematical representation of how changing one variable affects the other. So now that means the other variables that aren't involved in this relationship must be held constant. So for example, in Gay-Lussac's law, this is the pressure-temperature relationship. So first, before we talk about how pressure and temperature affect one another, this means that volume and amount of gas are still present, but they just must be held constant. So if we're evaluating pressure and temperature, we'd have the same amount of gas in the same container. We would make sure that amount of gas and volume did not change in any way. Now, this brings me to the emphasis I placed on understanding where pressure comes from. I think that if you understand pressure, then the relationships between the other variables become pretty intuitive. So, for example, the pressure-temperature relationship. So, think for a moment, how is pressure going to change when you increase temperature? Hopefully you thought that if I increase temperature, my pressure is also going to increase. If I think about pressure, the collision of the gas particles with the walls of the container, as I increase temperature, those gas particles are going to start moving faster. If the gas particles are moving faster, that means they are going to collide with the walls of the container more frequently and more forcefully, meaning the pressure will increase. So pressure and temperature are directly proportional. As one increases, the other increases. So this is basically how all the gas laws work. Now, we're going to talk about equations and plugging values in and solving for unknowns, but it's really about these different relationships. Boyle's law was the pressure-volume relationship. If you think for a second about how these are going to affect one another, if I have a volume of a container and I decrease the volume of the container, the pressure is going to increase. Okay, volume, decrease the volume, the pressure is going to increase. Why? Because pressure, collision of the particles with the walls of the container, are going to happen more often because it's a smaller container. So pressure and volume are inversely proportional. As volume decreases, pressure increases. Volume, temperature, Charles's law. So this one doesn't have pressure necessarily in it, but still thinking about pressure is going to help me through here. If I increase the temperature of my gas, I know if I said a moment ago that would increase my pressure. but we need the pressure to stay constant so we can evaluate what that does to our volume. So in order for the pressure not to increase, what would I have to do with the volume? I would have to increase the volume. Okay, so it's still that understanding of pressure really helps me to understand the volume temperature relationship. Increase in temperature would increase my pressure. So in order to make sure my pressure doesn't increase, I need to increase the volume of my container. So again, temperature and volume are directly proportional. Volume and moles, okay? So again, if I increase the amount of gas I have, that would increase the pressure. More gas molecules mean more collisions with the walls of the container. So to minimize that or make sure the pressure doesn't increase, I would need to increase the volume of my container. The last one I have listed here takes into account pressure, volume, and temperature, and it's derived from the relationships that we just talked about. Now, I actually like to think about all four variables in one expression, and that's what you see in front of you here. Now, this is not a gas law per se, none of the named gas laws I just went through, but it is how all the variables are related to one another and put into a mathematical expression. I think if you memorize this expression, you do not necessarily need to memorize each individual equation, Gay-Lussac's equation or Boyle's law equation or Charles' law equation. While you should know who's responsible for each of those, or if referred to as the pressure-volume relationship, you should know that's Boyle's law. I don't think you need to necessarily know each separate mathematical representation if you just think of this one. Because here's how I approach a gas law problem. I have some examples here. I would suggest as you read through the problem, we're still focusing on what's the problem asking for, what is the problem giving me, like we have all the way through the year in chemistry. But as I read through this problem, I'm going to label the numbers that I come across as I read. So, for example, if 22.5 liters, that's the first volume, at 748 millimeters of mercury, that's the first pressure, are compressed to, that's my second pressure, at a constant temperature. So that tells me temperature is not a part of this expression because it remains constant. What is the new volume? Okay, so now I'm at the point where I can take a second and look at what I've labeled in my problem. I've labeled volumes and pressures, and if I refer back to this expression with all four variables, if I only have pressure and volumes in my problem, that means temperature and amount, T and N, I can get rid of those. And so I'm left with an expression of P1 V1 equals P2 V2. Now I can just pull the numbers out of the problem and plug them in. I've already labeled them there. So we said P1 is 748 millimeters of mercury. V1 is 22.5 liters. P2 is 725 millimeters of mercury. And V2 was what we were looking for. Okay, quick multiplication and division, and I can get my answer for my new volume here. One quick note about units. Your units need to be the same. So in this case, it worked out because both my pressures were given to me in millimeters of mercury. Should one pressure be in millimeters of mercury and the other one in, let's say, atmospheres, I would need to convert one to the other to make sure that they're the same. On that same note, when I solve this problem, V2, the unit is going to be in liters. Okay, next I get to the next gas law problem. I reset and do it all over again. A gas occupies, well, that's a volume at a temperature. What is the volume and temperature? Okay, so now I look at what I've labeled here in my problem. I've labeled volumes and temperatures. So if I go to my expression, and therefore that means I can get rid of pressures and amounts, and I'm left with an expression that looks like V1 over T1 equals V2 over T2. Okay, remember the one thing to add here is my temperatures, while they're listed in degrees Celsius, that's how they were recorded, I must first convert them to Kelvin before I plug them into the expression. So 273 plus 0.15 plus 27.0 to get my temperature values in Kelvin before I plug them in. I'm just going to jump ahead and show you one more thing here that I want you to make you aware of, and that is the idea of standard temperature and pressure, STP. I'll scroll up here for a quick second because I've listed that information here, standard temperature and pressure. So what are those? So one, we need to catch in problems that those are telling us values. That's quantitative information. The standard temperature is 273.15 Kelvin and standard pressure is 1.0 atmosphere. In the pressure video for chapter 8, section 1, I listed the standard pressure values at a number of different pressure units, PSI and pascals and millimeters of mercury and torr. All of those values are standard pressure. Okay, so depending on what pressure unit you have, you can pick the standard pressure that you need. The reason why I point that out is because it becomes important for us to make sure we catch that, because often that data will be listed in that way in a problem. For example, this one here. A gas has a pressure of, so P1, at a temperature of T1. What is the pressure, P2, at standard temperature? So we have to recall that that is an actual, that is a number, that is a value that I need to catch. So sometimes it'll be written like that. Sometimes you'll have a problem that references STP. So that would give me a temperature and a pressure value. So my point here is we just can't miss those words and think that we don't have enough information or enough data to solve the problem. The last gas law we're going to talk about in this video is the ideal gas law. You can see the ideal gas law is written here. PV equals nRT. The variables don't change. What you notice here is we have all the variables together and one of each of them. So we're not evaluating how a change in one variable affects another like we did in the other gas laws, but we're seeing how what the result is for whatever unknown variable given the information on all the other variables. That means we need a constant. That's the R, the ideal gas constant. I've listed it here for you in two ways. You can see the difference in these two is the pressure unit. Okay, so 0.08206 is when we have a pressure in atmospheres. 8.314 is when we have a pressure in kilopascals. If you have a pressure in something different, you have to convert it to one of these two pressure units and use the appropriate constant. You can see the other variables in here. Your volume is in liters, your amount is in mole, and your temperature, as always in the gas laws, is in Kelvin. So because we're using these constants, those variables must be in those units. So if they give me volume in milliliters, I have to convert to liters. If they give me amount in grams, I have to convert to moles. Okay. By this point, we should already be comfortable with the idea that we need to convert to Kelvin for temperature. So I would approach an ideal gas law problem the same way I would any gas law problem. I'm not going to know ahead of time, hey, this is an ideal gas law problem. So I get a gas law problem, I'm going to read along, and I'm going to get to this, and I'm going to say, well, that's a pressure, that's a volume, that's a temperature, how many moles? So when I'm done reading, I take a look here and I see that I have one of all four variables. So that's my clue that this is the ideal gas law, PV equals nRT. Okay, pressure is in a unit that works, ATM. Volume is in liters, that also works. We're solving for N. So because pressure is in atmospheres, we're going to use this constant, And then, of course, temperature, I have to convert to Kelvin by adding 273.15 to put my temperature value in there and solve for N. That is a quick overview of gas laws. Important that we understand the relationships between the variables, but also that we can, in any given problem, be able to, what's the problem asking for? What's the problem giving me? Pull out the data and plug it into the appropriate relationship in order to calculate for the unknown variable. Now we're going to spend a good amount of time practicing gas law problems between now and our next meeting.